Let's continue on with the example we were talking about last time, where we were trying to find a Fourier series, pardon me, goodness, for f of x equals x on the interval from 0 to 2 pi. The idea behind this is that you'd have some sort of periodic function that you're trying to approximate, so you're going to use sines and cosines to be able to do that. Remember that we will need to calculate those Fourier coefficients for each of our terms in our trig polynomial. So the first one is just 1 over the square root of 2 pi, integral from 0 to 2 pi of the function, whatever function we're trying to approximate. For the a's, we use those as our coefficients on the cosines. So we'll integrate the f of x times cosine of nx dx. The b's are your coefficients on the sine. So almost the exact same integral, just using sine rather than cosine. So those were our coefficients we talked about last time. Remember where these are coming from. We're using the fact that in our continuous functions over the interval from 0 to 2 pi, if I look at the functions 1, cosine x, cosine 2x, all the way out to cosine nx, and then do the exact same thing for sine, this is an orthogonal basis. You can convert it to orthogonal. It's orthogonal with respect to that inner product that we talked about, where you do the integral over the interval of the product of the two functions. That's our inner product in that continuous function space. That's an orthogonal basis. The magnitude of 1 is square root of 2 pi, which is why I've got the 1 over square root of 2 pi in front of the constant term. And then the magnitudes of each of the others are square root of pi, which is why we've got the 1 over square root of pi in front of each of the other ones. Okay. So what we're doing here is we're computing projection of f of x onto this subspace by using inner products. That's what this is. Okay. We talked about that. All right. It's a lot of computation, so typically we go to something in the land of technology to help us out. I'm on GeoGebra here because GeoGebra has a computer algebra system built in where I can do these a little bit more exactly. So I did this right at the end of class last time. I want to integrate. The function we were trying to approximate is x. Let's do the cosines first. So I'll do cosine of n times x. Let me see if I can zoom in a little bit, perhaps. That was big. Got it now. All right. X times cosine nx. That's the integral I want to do. I'll worry about the constant at the end because that's easy to take care of. I want to integrate with respect to x, and I want to go from 0 to 2 pi. This looks nastier than it is. We talked about this right at the end of class last time. Remember, the period is 2 pi for sine and cosine. So this is just multiples of the period. So is this. What's cosine of 2n pi, no matter what n, as long as n is an integer? What is cosine of 2n pi equal to? 1, right? Because that's the same as cosine of 0. Sine of 2n pi is always equal to 0, right? So this term's going to go away. This is just a 1. We have 1 over n squared minus 1 over n squared. So what's this integral always going to be? For any n? 0, right? I've got 1 over n squared minus 1 over n squared. It's always going to be 0, no matter what. Okay? So all of the coefficients on the cosine are 0. Okay. Let's do the same thing for the sine. the function is going to be x times sine of n times x. Again, remember, if you're using GeoGebra to do these, I'm not going to expect you to do it by hand by any stretch. If you're using GeoGebra, remember, I can't use n, x right next to each other because it'll just treat it as a new variable. It understands the space between as being multiplication. Or if you want to be double sure, put a multiplication symbol in between. Okay. Just don't write your n and your x next to each other because it's going to treat it as a new variable. Okay. X is, pardon me, x is the variable we want to integrate with respect to 0 and 2 pi. Again, looks a little nasty, but let's just make sure we know what all these terms are. Sine of 2n pi again is 0. That's 1. So all we have is negative 2n pi over n squared. Right? The n's will cancel, so you just get negative 2 pi over n squared. Okay. So in this case, for this particular problem, we did integral from 0 to 2 pi of x sine of nx dx and got negative 2 pi over n, right? That's what it says, isn't it? Okay. That's almost our b sub n. We got to multiply by 1 over root pi. I'll do that in a minute, okay? That's almost our bn, but we got this part, right? Now let's figure out our constant. Our integral of x, because it's just f of x for this part, right, for the constant. This one you probably do by yourself. I don't have, in GeoGebra, if you've only got one variable, you don't have to tell it what variable to integrate with respect to. It'll know. Just went ahead and typed it because it matches the other form. I get 2 pi squared for that one. Okay. All right. So we found our coefficients. So let's see if we can create a polynomial or a trig polynomial that will get us close to what we want. So I'm going to use in GeoGebra the sequence command. Let me show you how that works. First thing I want to do is I want to define a function. Let me zoom out just a smidge so it's not underneath whatever's on the screen there. There we go. I want to define a function. I want to use this function later. In particular, I wanted to graph it. So I'm going to define a function. I just give it a name and an input. Right? Okay. Colon equals. Make sure you put the colon in there so it knows that you're actually defining a function. Okay. It's a little crabby about it if you don't put the colon. All right. Let's do the constant first. That constant is there in line 3. So I can actually refer to the lines as just the number 3. Just use a number sign, hashtag, whatever you want to call it. What do I need to divide that 2 pi squared by? Well, that coefficient out in front, right? So we'll do square root, which is SQRT of 2 pi. That was the constant term, wasn't it? The rest of them are a sequence. The sequence is going to get multiplied by the 1 over root pi here. So I'll do 1 divided by square root of pi. And then I'll multiply that by a sequence. So let me show you how the sequence command works. Here we go. That's the one I want. All right, what expression do we want? Well, we already said that, and I was going to type it in. We already said this one was 0, and this one was negative 2 pi over n. That's the one I want, right? So we'll do negative 2 pi over n. What do I want to multiply that by? That's the coefficients on all the signs, right? So I'll take that times sine of n times x. In this case, the variable that we're adding up is n. And let's just create maybe 10 terms here. This should give me my Fourier series when I do this. Okay, this should give me a function of x. And when I'm done. Okay, because all it's going to do is plug in the numbers 1 through 10. Oh, I gotta do something else. I lied. I made a sequence, but I didn't make a sum with this. Sorry. Go back in front here. I gotta add these up. There we go. I made a sequence, but I didn't add them. Okay. Now that should do it. There it is. Oops. Now let me go back over here. And hopefully... now it says I got an issue. There we go. Should... It's not quite right. Remember, we were trying to approximate f of x equals x, right? I've got the approximation, it's just in the wrong spot. How do I know it's in the wrong spot? Well, my f of x equals x should be going here, right? So something's not quite right. We'll fix it here in a second. We'll go back through and make sure we've got everything in here correctly. Right. But do you see what it's trying to do here? Again, we're trying to approximate a periodic function, right? So it's f of x equals x from 0 to 2 pi, and then it repeats. So if you were thinking about what the function looked like, your function would look like x and then stop at 2 pi, and then repeat again, and stop at 4 pi, and then repeat again like that. And so what this is doing is it's taking that trig polynomial, that sum of the trig functions, and trying to approximate here, but of course when I get close to the edge, I have an issue, don't I? So it's trying to connect a continuous function with a discontinuous one, which is why I got that jump. Now again, my constants are off somewhere because we should be matching this up pretty well. But what it's doing is it's trying to approximate here, and then it'll jump, and then it'll do the same thing here. It'll approximate as well as it can until it gets towards the end, and then it'll jump and keep doing that over and over again. That original function, if we think about just being f of x equals x and then repeating, is referred to as a sawtooth wave. This is a pretty standard function to try to approximate with a Fourier series. Let's see if we can figure out where the error is. Let's see. We did x from 0 to 2 pi and divided it by 1 over 2 pi. Yeah, makes sense. Okay. And then what do we do here? So it was negative 2 pi over n times sine of nx. Looks like it's shifted too high. Don't know why. It's like it's up a little bit. It's also too tall. Not sure why it's off. Shouldn't be off. Those are the right coefficients. I added them up. Just trying to see if it did anything goofy with it when it added it up. No. Because we took the constant, which is there. Oops, can't really see what I did. Pull the screen back down. Sorry about that. 2 pi. Now, you know what? I'm not going to spend much more time on it because it's a constant error somewhere. You can get the idea of what's going on. Let's do the one that's on the back side because I want to do some new stuff today anyway. So the next one is a piecewise defined function, right? You do the very, very last one, where we've got that function. It's 5 from 0 to pi and negative 2 from pi to 2 pi. So we'll have to do this one in a couple of pieces. So let me jump back over here. Let me turn that one off. Come back over here. All right, zoom back out a little bit so we can see. All right, well, maybe. All right. All right. So let's see what happens here. My function is just 5 and 2, all right? So if I do the first one here and do integral of 5 times cosine of nx, variable is x, and I want to go from 0 to pi. What's that always going to equal? That one's always 0, isn't it? Okay. And if I do integral of 2 times cosine of nx, and then x and pi to 2 pi, what's that going to equal? Also 0, right? Okay. So notice again, just like the previous one, I'm not going to have any constants multiplied by my cosine, so I don't need to worry about that one, right? All right, so let's do the same thing for sine. I want to do 5 times sine of nx, where my x goes from 0 to pi. That one's going to alternate, right? Because your cosine's going to go -1, 1, -1, 1, -1, right? Notice that when it's equal to 1, we end up with 0 again, don't we? But I'm just going to leave it, and I'll let GeoGebra handle that. Okay. Now do the same thing for 2 and pi to 2 pi. So same command, integral of 2 times sine of nx. X goes from pi to 2 pi. And we get something similar, except this one's always going to be 1 since it has a cosine squared in it, right? Yeah, I'm not too worried about simplifying it in this case because I'll just let GeoGebra handle it. All right. So far, so good with getting them put in here? Yes. Where am I getting them? Remember, we're trying to do projections onto the subspace generated by this. These are our formulas always for the coefficients. Okay, because they're going to be the projections of the function that we're using onto the subspace generated by these things. Okay. All right. I also need the constant, but the constant's not too bad. I should be able to do that one by hand. It's 5 from 0 to pi, and it's 2 from pi to 2 pi. Oops. And again, the constant is just integrate the function. Well, if I integrate 5 from 0 to pi, what am I going to get? 5 pi. If I integrate 2 from pi to 2 pi, what am I going to get? 2 pi. So if I add those two things together, I'll get 7 pi, right? That one's not too bad to do because it's just a constant function. Okay. All right. So now let's make our function. I'll give it a. I thought I turned that off. Turn that off. Go away. Oh, I wonder if it messed it up. Nope, that's not what happened. Okay, never mind. Still don't know what happened up there. All right, let's define a new name. I'll call it G. Our constant, again, you just said was 7 pi. We need to divide that by the square root of 2 pi. There aren't any cosine terms. We have lots of sine terms. I need to do 1 divided by the square root of pi. And I'll multiply that by the sum of the sequence. The sequence command just makes a list, and then the sum command just adds up the list. You've done programming before. That's what it's doing. You can do the same thing on your calculators. Anyway, what's the expression we want? Well, I've got 2 of them, right? I need to take that integral that we, oops, sorry, not that one. This integral, there you go. This integral and the one right below it. That's covered up right now. Okay. So what do I need to do? I need to take that. Pardon me. I need to take. I'm going to do it in 2 pieces. Maybe I'm going to do it in 2 pieces. There we go. What are you doing? Sometimes GeoGebra is a pain. Okay. Try again. All right. So I need to add, pardon me. We need to do this expression that's in number 8. Oh my heavens. There we go. In number 8. And I need to multiply that by, I also need to do what? Those are our coefficients when we're in between 0 and pi. No, it's not. I just need to add them because I did 0 to pi and 0 to 2 pi. All right, so I need to take your number 8. That was the integral from 0 to pi, all right? And I also need to do number 9. That's the integral from 0 to 2 pi, or from pi to 2 pi. So if I add those 2 together, that gives me the integral that I want, right? If I take the integral from 0 to pi, add the integral from 0 to 2 pi, gives me the integral that I want. I need to multiply that by sine of nx. The variable we're adding up is n, and again, let's do 10 terms. Oops, so I'll go from 1 to 10. And I don't need the increment on there. Okay. Again, I'm just pulling the 1 over pi out because that's going to be on the integral, right? So it's going to be on every single term. So I'm just pulling it out in front and multiplying it out by the sum. So again, just to recognize the syntax, this was the first half of the integral we computed. That went from 0 to pi. This is the second half of the integral we computed from pi to 2 pi. To get the whole integral, I need to add them together, right? Well, that's what we need to multiply by the sine of nx. I've typed up everything correctly and hit enter. And my thing is still shifted. Why is everything shifted? It's driving me crazy. It's not like I haven't done these before. All right. In any event, you can, again, I don't know why everything shifted. I'll get it fixed and send an email to you when I get it fixed. I don't know why everything shifted. But you can see what it's doing. I hope, right? Part of your function is up at 5. This would be at 5. Like I said, everything is shifted and stretched, and I don't know why it's shifted and stretched. Something goofy is going on when we're doing these integrals. But in any event, this should be at 5. This should be at 2. So the function is trying to approximate it up here. That's why it's waving around because you're using trig functions, right? It's trying to approximate this part here, and then it jumps down and approximates this part here, and then it just keeps doing it over and over again because it has a period of 2 pi. So it's going to jump back and forth. That's the idea behind Fourier series. They're good at approximating periodic functions. That's the idea. Okay. But also notice that something bad happens at the boundary, doesn't it? It's having a hard time approximating it at the boundary. It's also shifted up for whatever reason, and I don't know why. Like I said, I'll do it after. I'll get it done after class and send you an email and try to figure out what's going on. In any event, notice it has a hard time at the boundary. And if you've done anything with differential equations, you know boundary problems can be hard. Okay? It's the same idea here. Anytime you're trying to approximate a discontinuity with something that's continuous, you're going to have issues. That's kind of the point here. But, again, this is a nice way to approximate something here that kind of mimics turning something on, turning something off, turning something on, turning something off. It's jumping from one level to another. Besides the fact that I can't get the numbers to come out right, does the process make sense what we're doing? Just this, it's the same thing over and over again. It doesn't change. Okay. I would not expect you to do one like this by hand on an exam, but it is a nice application, which is why I wanted to talk about it. It's an application of least squares that we don't see in too many places, so I want to make sure you see it. Yes?
When you did number 8 plus number 9, why can't you do, oh my gosh, Could you do 0 to 2 pi instead of adding the 2? Because that's essentially what you did, right? Going from 0 to 2 pi.
But my function changed, right? My function jumped from 5 to 2.
Oh, okay. Yeah.
Yep. That's why I have to do it in 2 pieces because I have a piecewise defined function. What I'm not understanding is why my constants are all off. They should not be off that much. Well, they shouldn't be off at all. So, like, there should have been a negative in front of the 2. You're right. Yep, it went from 5. Yeah, the problem actually said -2, didn't it? That's not going to help. That's not going to change the other pieces, unfortunately, but it should have made it jump a little bit more. But yeah, I mean that's a better answer. It should have gone from 5 to 2 anyway when I had the wrong number in there. But I could fix it. That fixed that part. Anyway, I'll figure out what's going on. I don't know why it's not doing the right thing. Anyway, is the process okay? So they can actually go do something new. All right. Let's switch gears a little bit. I don't know what's going on. Showed me problems multiple times. I don't know why it's not coming up that number. I got something slightly off when I entered it. It's doing the right thing for the approximation. It's just not doing it at the right values. So clearly, I've got something goofed up in the value somewhere. All right. So we're going to shift gears a little bit and talk about linear transformations in the next chapter here. So section 6.1 talks about an introduction into linear transformations. So you see linear transformations a lot. Linear transformations, to give one explicit example of why they are important, they pop up in computer graphics quite a bit. Well, transformations in general, but linear transformations are ones that pop up as trying to rotate things, trying to stretch things out, trying to shrink things. Those are kind of our linear transformations. There are other types of transformations as well, but linear ones are what we're going to talk about in linear algebra. You can talk about other types of transformations in other contexts, depending on what you're trying to do. All right, so what do we mean by a linear transformation? Well, we're going to have a function to start with. If we're not familiar with the function notation, remember this is just the name of the function. This is telling you what place your inputs are coming from. This is telling you where your outputs end up. That's all the notation means. Anyway, we've got vector spaces. So a linear transformation is a function from one vector space to another, but it needs to satisfy a couple of properties. The first thing that it needs to satisfy is that it needs to break up over sums. So it doesn't matter if you add first and then do the map, or do the map and then add. Okay. We've seen a property like this with the distributive property back when we talked about vectors, either inner products or vector spaces. When you've got the distributive property, remember that in particular when we distributed over constants, if you had a constant sum, and then if you did the constant sum first and then multiplied, you ended up with a vector. Versus if you did the multiplication sum and then added, that was adding two vectors, right? So it was the addition was taking place in different places. Same idea here. This addition is taking place in V. This addition is taking place in W. All right. The second property that has to be satisfied is that if I have a constant, I can pull the constant out. Oops. Okay. Doesn't matter if I do the scalar multiplication and then the map, or the map and then the scalar multiplication. That's what that says. All right, so the names that we use for V and W are the same names that you've used before, just like for any function. So the V is the domain space, W is the codomain space. Remember, not all functions are onto their outputs, right? Well, we have a different name for codomain versus range. We'll talk about range in a little bit. If you hear about image and pre-image, the image of V is simply just the output. Is what you get when you plug V into the function. Now, again, it's a function, right? So if I put one thing in, how many things am I allowed to get out? Just one, right? Put one thing in, I get one thing out, right? However, if I have something that came out, does that mean only one thing mapped to it to start with? No. So when I talk about pre-image, this is going to be the set of all vectors in V such that T of V equals W. It's everything in the domain that maps to W. That's the pre-image. So to give, not with linear transformations, but to give a specific example of the difference, if I have the squaring function, the image of 3 is what? I talked about the squaring function. The image of 3 is 9. The pre-image of 9 is what? 3 and negative 3, right? Because both of them map to 9. Right? Does that make sense? Okay. All right. So let's talk about some examples of things that are linear transformations. So if I want to show something is a linear transformation, I would need to show those two properties. So the first property is that I need to start with two vectors in R3. So I'll say I have x1, y1, z1, and x2, y2, z2. It's a 2 in R3. I need to show that my transformation breaks up over the sums. Okay. This is going to be a lot like when we were doing kind of verifying vector space axioms or proving things are subspaces, right? Showing that those closure things are satisfying those different axioms. This is the same kind of idea. If I want to do the transformation applied to the sum, what do I need to do first? Do I do the transformation or do I do the addition first, the way it's written? The addition, right? So I need to do T of x1 plus x2, y1 plus y2, z1 plus z2. Now apply the transformation. What is this going to equal? This is T of that thing, right? So now it just says plug it in. So what do I get when I plug it in? Okay. Good. Oops. Good. Yep. That's what we get when we put it in the first component, right? The second component will have negative of y1 plus y2 plus 5 times z1 plus z2. I'll write it below since I've run out of room. 4 times x1 plus x2, 7 times y1 plus y2 minus z1 plus z2. Oops, sorry about that. This notation just says plug this number in for x, that number in for y, that number in for z, right? We've got lots of places to plug it in. Okay. We could simplify that and split it back apart, or we could do the other part of just compute the other side of your equation. I could do t of x1, y1, z1 plus t of x2, y2, z2. And see, we end up with the same thing. That's our goal, right? If it's going to be, I'm trying to show this really is a linear transformation. I need to get to the same thing on either one, right? So this one will be 7x1 plus 2y1 minus 8z1, negative y1 plus 5z1, 4x1 plus 7y1 minus z1, and then literally the exact same thing except with subscripts of 2's, right? Right, just plugging those in. Basically, I wrote the transformation over twice, just with some subscripts rather than the variables that we started with. Now, what are we going to do? What do we do now? We add them. Yeah, it says add them together, right? When we add, I can put my x's together. I can put, yes. It should be a plus. Yeah, that one. Yeah, thanks. And then I can put the y's together. And I can put the z's together. Do the same thing in the second component. Put the y's together, put the z's together. And then the same exact thing in the last one. Bless you. And now again, look at your two answers. Are those two things the same thing? Yeah, because I can either think about distributing each of the constants and seeing this, or factoring out all the constants and seeing that, right? Those really are equal to each other. So that shows that we have the first property satisfied, right? That it breaks up over sums. What's the second property? Yeah, the constants pull out, right? So I have a t times c of x, y, z. I would put that all the way, oops, sorry. First thing I would do is multiply that, wouldn't I? I multiply the c through the vector, so I'd have cx, cy, cz that we need to take the transformation of. Now I'm just going to replace the x, the y, and the z with a cx, cy, and cz. I've got a c everywhere, don't I? So I could pull the c, first I could pull the c out in each of the individual components. And then since I have the same c in every single component, I could pull the c out of the whole vector. And that really is C times T of X, Y, Z. A lot of work to get there. I don't disagree. But that's how you show that something is a linear transformation. Now, later on, we'll be able to recognize that it's a linear transformation based on its form, and then we'll use the form to be able to write it in a different way, which will be able to do some manipulations with things. This is similar to things we've done before, isn't it? Okay. All right. So let's look at a couple of other examples that wouldn't take nearly as long. Let's say you pick an arbitrary vector in Rn and then fix it, and then your transformation is just take the vector and do the inner product with a y. And we're going to pick a y, fix it. Our transformation for any other vector x then is just do the inner product with y. This one's a little bit easier to do, because if I start with t of x1 plus x2, what does the transformation say to do? What am I going to do with the x1 plus x2? I'm going to dot it with y, right? Right? What do we know about inner products with respect to sums? Yeah, they break up over addition. Good. Right? What's a better way to write the first one in terms of the transformation? T of x1, and the second one's going to be T of x2, right? I know this may seem a little bit strange, but you've dealt with functions like this before, right? Basically, it's just saying take f of x equals 3x, right? If the fixed number is 3, right? Instead of a fixed number, you're doing a fixed vector and then doing the dot product. It's the same kind of concept, right? Okay. We'd also need to show that I can pull the constant out. So if I have a constant times x, scalar times x, I would do the scalar times x dotted with the y, but what can we do with the scalar now? With respect to inner product? Yeah, you can reassociate essentially, right? Pull the c out, and then the second piece is the transformation applied to x. That okay? That's the idea of how you would prove these things. Without going through the next example, what makes the next example work? Well, notice if you put a sum in here, I should have used this. Should be that should be a T. That should not be a C. There's a typo. This should be a T. Sorry about that. That's a typographical error on my part. If I put another f of x plus g of x inside here, where does it go? So I have f of x plus g of x, where does it go? In the integral, right? But what do we know about integrals with respect to sums? Yeah, they break up, right? And then so you just have the transformation of each piece. What if I had a constant in here? Well, then the constant would be inside, but what can you do with the constant? Pull it out in front, right? So that's just basically properties of integration, right? Okay. All right. So same concept there. All right, so this one's going to be one of our important ones. And it's going to be a transformation that is realized through matrix multiplication. So when we have a given matrix, we call say it's an A, we use the notation T sub A to denote that we are doing matrix multiplication with the vector V. Okay? All right, so the question I have here is not whether or not it's a linear transformation, because we know that matrix multiplication will distribute over sums and constants will pull out to the front, right? So the problem's not with the linear transformation. What I want to know here is what's your domain and what's your codomain. Okay? If I have an M, if this is an M by N, Where does this vector, what size does this vector have to have if we're going to do matrix multiplication? It's going to have to be an Rn. It's going to be an n by 1, right? To make the columns match the rows, right? So your input space then is going to be what? What's your domain going to be? R what? Rn, right? Okay. When you do the multiplication, what size does this have? Yeah, it's an m by 1, right? So that vector is going to live in Rm. So notice, in particular, notice that number of rows here corresponds to the dimension of the output. The number of columns here is the dimension of the input, right? It kind of flips, it looks like it flips it around. At least I think it looks like it flips it around. Is okay? All right. We're going to use this later on. That's important, okay? All right. How about some things that may or may not be linear transformations? Let's look at your next page here, whether or not they're linear transformations. Remember, if it's a linear transformation, we need to be able to break up over sums and be able to pull constants out, right? This is put in a vector, take its magnitude. Do magnitudes break up over sums? I don't believe they do they? Okay. For example, so just in general, we should be able to pick a whole bunch. There are some that do work, but we should be able to pick up a whole bunch that don't. Okay. For example, if I do 1, 0 and 0, 1, right? What's the magnitude of 1, 0 and 0, 1? What's the magnitude of each of those? 1, good. What's the magnitude of 1, 1, which would be the sum of those two vectors? Root 2, right? Is this plus this equal to that? No. Okay. Some vectors work. Most of them don't. Okay. All right. So they're not equal to each other. So that's not true in general. All right. How about the next one? So let's take n by n matrices and map it to the reals by the determinant. Is that going to be a linear transformation? No, again, doesn't break up over sums, right? In general, determinant of A, oops, not D, DET, determinant of A plus B is not determinant of A plus determinant of B in general. So again, both of those are no, right? How about transpose? Yeah, that one will work okay, right? Because if I do A plus B transpose, the transpose does break up over the sums. And if I do a constant times a matrix, the constant will pull outside of the transpose as well. So this one works. This one breaks up over sums and constants pull out. So transpose is a perfectly fine linear transformation. The last one, the reason why I put this last one on here is because it kind of reminds you of something being linear, right? When we talk about linear functions in algebra class, Usually that linear function you try to write in an mx plus b form, right? We call that a linear function because its graph is a line. Unfortunately, even though I've got this plus 1 here, which makes it feel like a linear thing, this is not a linear transformation, okay? Because if I do p of x plus q of x on the inside, I would have p of x plus q of x plus 1, right? But if I do the transformation of p of x plus the transformation of q of x, what ends up on the end? A plus 2, right? Okay. So this right here is causing an issue, okay? So just to write it down, transformation of p of x plus q of x would be p of x plus q of x plus 1, but the transformation broken up would be p of x plus q of x plus a 2, okay? So that makes the transformation not linear. These are not the same thing, right? Okay. So it's not a linear transformation. So again, the whole reason why I put this on here, there's a difference between a function being a linear function from what you talked about before versus what a linear transformation is. Okay? You're used to having plus constants stuck on the end, and it doesn't change the fact that it was a straight line, right? Okay. So it'd be a little bit careful with that, which is why I wanted to put that one on there. All right. We'll do more with linear transformations next time. In particular, we'll prove some properties, which won't take that long. By the way, you might be able to guess how to start this. If I started with the left-hand side, what do you think I would want to do with that 0 on the inside? Make the 0 equal to 0 plus 0, right? Some stuff we've done before, right? So that was a same tried and true trick we've done before. So, all right, we'll do more of this next time. Have a good one. I will also get you that